linear programming problem that we started with. All variables were non-negative. And then we said the following, that this is a standard form linear programming problem. So we are going to not worry about the objective function in the sense that all objective functions that we deal with are maximizations. And then we are going to forget about non-negativity constraints because these are implicitly there in any standard form representation. And we observe that this can be written in a particularly nice form. We could view this equation as, or we can rewrite this as x3 equals 5 plus x1 minus x2. Similarly, x4 was 35 minus x1 and 3x2. And x5 is 20 minus x1. And then to capture the objective function, we just introduced a new row, and let z be 0 plus 2x1 plus x2. Okay? So this is the first step. And the rationale for doing this is the following. So we assume that we are free to determine the values of x1 and x2. We can set them to anything we like. And if you do so, the values of x3, 4, and 5 are determined by these equations. Okay. And for any value of x1 and x2 that you use, you get paid 2x1 plus 3x2. Of course, if these are the only restrictions, you would set x1 and x2 to be as high as you can. The only other constraint is that they have to be non-negative, which of course you would do. The only difficulty is that you also have to have a constraint on the values of x3, x4, x5, which are determined by your choices of x1 and x2. So if I set x1 and x2 to both be 100, then you can see that this, for instance, would become negative. And that's why you're not allowed to do that. Okay? So of course, this is just restating the problem, right? This is exactly the problem that you started with, which is saying what values of x1 and x2 should I use so that I make this as large as possible, and so that x3, x4, x5 are all non-negative, which is the same as saying so that your choices of x1 and x2 satisfy the original constraint. So we've done nothing more than restating what the problem is at this step. Then the second step is, rather than guessing what values we should use, we just go about changing the value of exactly one of the variables while keeping the other one fixed at 0. Okay? So again, the assumption is that this representation really captures the solutions in which x1 and x2 are both set to 0. So here on, we'll assume that anything to the right of this equation, any variables there are set to 0. And you can read off the current solution just by looking at these numbers. And starting from this particular solution, which is x3 equals 5, 4 equals 35, and so on, we want to now move to a different solution. And the way we are going to do that is by a very simple step, which is that we are going to fix the values of all but one of the variables, and think about increasing the value of that one variable. So here, I think we decided to increase the value of x2. So this is what's called the entering variable. So x1 will be held at 0, and x2's value will be gradually increased. And of course, for every unit increase in the value of x2, you get paid $3. And we agreed that we'll make x2 as large as possible. Increasing x2 does not affect x5 in any way. Increasing x2 affects x4 in the sense that x4 is now going to go down by 3 for every unit increase in x2. So this equation says x2 can be increased up to 35 divided by 3. if you increase x2 beyond that, then x4 will have to become negative under the ground rules that you set for yourself, which is x1 remains at 0. Okay? So again, the consequence of making these simple steps is that it's very easy to evaluate the effect of the change that you're making on these variables. So you just have to look at the constant and the coefficient of the variable whose value you're increasing. If that coefficient is negative, then you get a certain limit on how high that value, that the increase can be. Similarly, this says that x2 can go up to 5, but no more. Now, as you're gradually increasing x2 from 0 onwards, you're going to hit this boundary before you hit this, and therefore this is the constraint that's going to limit you from increasing x2. So if you've already seen the simplex method, this is what we are doing here is called the minimum ratio test. And if you haven't seen it before, just know that what we are doing here is called the minimum ratio test. So this is where we left off towards the end of the previous lecture. So we decided to increase the value of x2. This is not affected. This says you can go up to close to 12, and this says you can go up to 5. This is the most limiting, so we go up to 5. Now we want to transform our system so that it reflects the new solution that we are at. Okay? So just as this set of equations captured x1 equals 0, x2 equals 0, 3, 4, and 5 given by these, we want another system that captures x2 equals 5, x3 equals 0, x4 equals 35 minus 15, which is 20, and x5 equals 20. And the features of such a system are the following. The dependent variables, I should say each dependent variable occurs in exactly one equation with a coefficient of 1. So if you notice, x3, which is a dependent variable, occurs only in this equation, and there is no other x3 anywhere else in your system. Likewise for x4 and x5. Yes?
I'm just confused. What's the difference between a dependent variable, independent, and the basic and the non-basic? I didn't tell you about basic.
So we'll get to that in a moment. Okay. For now, I'm just calling these dependent and calling these independent because these are the variables whose values we set, and we always set them to 0. And these are the variables whose values are determined by the system of equations. So each dependent variable occurs in exactly one equation with a coefficient of 1. That also means that every dependent variable is expressed in terms of independent variables. Each dependent variable occurs in a distinct equation. So you don't have an equation in which there are two dependent variables. So these are the only two properties that we want. And in fact, I very quickly wrote down the system that would correspond to the new solution. So let me rewrite that and then we'll start the new stuff. So the way you would you would go about achieving such a transformation is to start with the equation that limited your increase. Okay? So this is the equation that stopped x2 from becoming any larger. Start with that equation. That equation is going to give you a new dependent variable. So, for instance, from here, x2 its value is being increased, and therefore x2 is going to be the new dependent variable. So we start with this equation and rewrite this in the form that we like. So there is very simple. I would just say x2 is just 5 plus x1 minus x3. So this step is actually, we go from a set of dependent variables to another set of dependent variables, where the new dependent variable is the one whose value you choose to increase, and the old and the variable that was dependent, that now becomes independent, is this one. So after this step, you're going to call x2 dependent and x3 independent. So we use the word dependent and independent. It's also common for us to use the following words. So dependent variables are called basic variables for reasons that will become clear a little later. And independent variables are called non-basic variables. So anything on this side, these are non-basic, and these are basic. Okay? So in this language, in a system of equations, every basic variable occurs exactly once with a coefficient of 1. And every basic variable occurs in a different equation. So you look at any equation, it'll have exactly one basic variable. This, we said, is an entering variable. It's called an entering variable because this variable is now going to become basic. It's going to enter the basis. So this is the new basic variable. And this one here is the leaving variable. So again, in this language, which is the more common terminology, x3, x4, and x5 are basic variables for this system. x1 and x2 are non-basic variables. Non-basic variables are always held at 0. And in a simplex iteration, you're going to, among all non-basic variables, you're going to pick one which you choose to enter into the basis. You choose as a candidate for entering the basis. And once you make that decision, the system of equations will tell you which variable leaves. So here, this we wanted to make basic, and x3 leaves the basis. And this is one iteration of the simplex method, and we are doing what is called a change of basis. So our new set of basic variables would be x4, x5, and x2. So new basic variables are x4, x5, and x2. And anything that is not basic is non-basic. So once again, now we want to rewrite the system such that every basic variable appears exactly once with a coefficient of 1, and each basic variable occurs in a different equation. And the way you do that is by looking at the equation, at this equation, which is sort of special, which is what limited the increase of x2, and rewriting it in a way that we want. Okay? And that's this. Now notice that if you go back and look at the other equations of your system, you can actually achieve what you want by looking at that equation, and wherever x2 occurs, we just plug in this. Okay. And now it will be in terms of all of the new non-basic variables. And when we did that, we got the following. We got x4 equals 20 minus 4x1 plus 3x3. We got x5 equals 20 minus x1, and we got z equals 5x1 minus 3x3 plus 15. Okay. So of course you can write this in a more convenient way. This is 15 plus 5x1 minus 3x3. And that's the new last row. So again, what does this say? So from this system of equations, we can infer the following. That this corresponds to the solution in which x1 and x3 are both 0. x2 is 5, x4 is 20, and x5 is 20. The current objective value is 15. This is the value of the current solution that you're at. Not only does it say that, it says if you increase the value of x1, you get $5 for every unit increase. And if you increase the value of x3 by 1, you get $3. I mean, you lose $3. Which is the same as saying if you decrease the value of x3 by 1, you get paid $3. Is that clear to everyone, the interpretation?
So when you when you first take the x3 as well, that slack variable or whatever, but the x3, the initial value of x3 is dependent on like x1 and x2.
Mm-hmm.
So changing the value in x1, does that result in changing x3 as well?
Okay, so the question is the following. If you look at the original system, x3's value was determined by x1 and x2. Now here it seems like x1 and x3 can be controlled independently. And that seems to contradict things, right? That's your concern. That really isn't an issue because you still have x2, which is one of the variables, right? You pick any value of x1 and any value of x3, an appropriate value of x2 would satisfy that equation. That's really what this says. Okay. Any other questions or comments? So this is just a slower version of what we hurried through towards the end of the previous lecture. But now starting from here, what would we do? So we said for every unit increase in x1, we get paid 5. For every unit decrease in x3, we get paid 3. So of course, we would like to decrease x3 as much as possible, but we can't decrease it any further than what it is. Right? It's already at 0, and every variable has to be non-negative. So the only way for us to improve things is by increasing the value of x1. Is everyone happy with that? And if we choose to increase the value of x1, what happens? So this is going to be the entering variable. And now we have to understand x1's effect on the values of all of these variables. So again, when I say that we choose to increase the value of x1, it's already determined that x3 stays at 0, so we don't have to worry about that. So this equation says that x1 can be increased up to 20. So this says up to 20. What about this? This says x1 can go up to 5. And what about this? This doesn't limit the increase of x1, right? If we increase x1, x2's value is also going to increase, and that's not going to cause anything for us. So this doesn't give us anything. So we saw there are two ways in which a variable's increase might not impose any constraint. One is, of course, that variable doesn't appear at all. Okay? Like when we increased x2 here, x2 didn't even appear, so this equation didn't care what you do with x2. Then the second way in which no constraint arises is if that variable occurs with a positive coefficient. So here x1 occurs with a positive coefficient, so increasing x1 is only going to increase the value of that variable, and we don't have any upper bounds. Okay? Yes, you had a question.
What is the value of x2 at this step?
So when we start, x2 is 5.
Okay.
Because these are both 0. Anything to the right of the equation is 0.
So we keep the value we found at the earlier step.
Right. We keep the value we found at the earlier step, and then we check whether there's a way to improve things even more. And we're going to keep on doing this until we can't do this any further. Yes.
And the second question, how did we pick that you're going to move the x1 variable?
So the question is, how did we decide that we're going to move the x1 variable? Well, I look at my objective function. It's 15 plus 5x1 minus 3x3. So this says that if I increase x1 by 1 unit, I'm going to increase my objective function by 5. And so that seemed like a good thing to do, so we decided to increase it. So to answer your question, anything in the last row with a positive coefficient is a candidate for increase. And if there are many choices, you pick any one. So, did that answer your question?
Yeah.
Okay. Good.
At the beginning, we chose x2 because it was positive, but we could have chosen the other one.
So yes, a follow-up question is, at the beginning, we chose x2. Could we have chosen x1? And the answer is yes, you could have chosen x1.
But as you have higher coefficient memory, that is more.
So is there any reason to choose x2? Any reason to favor x2 over x1? No. The fact that it has a higher coefficient, yeah, maybe, but that by itself doesn't mean anything, as we'll see in a little bit. Any other questions? Yes.
If the minimum ratio is the same, can you choose either one?
Okay, so that's a good question too. If there are many minimum ratios the same, can we choose any one? The answer is again yes, but it's a qualified yes, just as I said, qualified yes for positive coefficients here. You could choose any. I mean, you can pick anything, and eventually you will get to the solution. So the difference is maybe in how many steps it takes for you to find the best solution. So we'll worry about all of that in a little while. Yes.
So the only reason we couldn't change x3 because that was we used it in that equation over there.
No, actually, so the only reason why we couldn't change x3 is the following. x3 has nowhere else to go but up, right? Because it's already at 0. And if you increase x3, you're going to lose money, so you don't do it.
But
yes?
Did x3 turn into the leading variable only based on the fact that it was the most constrained equation versus?
That's exactly right. So did x3 turn into the leading variable only because it limited x2's increase in the previous step? the answer is yes. That's how you determine the leading variable. You have a question? No. Yes.
Well, this has to go with the first constraint, not the second one we got, right? So that not that x2 to 35/3.
Okay, so why did we choose to set x2 to 5 and not 35/3? That's because if we set x2 to 35/3, x3 will be negative. Okay, so you have to take the smallest number that you get from this test. That's why it's called the minimum. And it's a ratio because you divide this number by the coefficient of the variable that you're interested in. Okay. Anything else? Okay, so if we look at our new system, this says x1 can go up to 20, this says x1 can go up to 5, and so we are going to have to set x1 to 5. Actually, the nice thing is you don't have to worry about setting x1 to 5. You just have to remember that this is the equation that caused x1's value to be limited. Okay? So you just mark that, make that's a special equation. And now we are going to do a change of basis. Okay? So x1 is going to enter the basis, and x4 is going to leave. And to rewrite the system the way we want, we are going to now take this equation and rewrite it in a convenient way, which is so I'm going to take this equation and I'm going to say, okay, so I want to bring x1 to the left and bring x4 to the right. So 4x1 is 20 minus x4 minus 3x3. Okay? And from here, I get x1 equals 5 minus 1 over 4 x4 minus 3 over 4 x3. So I get this, and now I can express x1 in terms of the new non-basic variables. Now I go back to the remaining equations in my old system. Wherever I see x1, I'm going to plug in this value. And then I get everything in the form that I like. Does everyone see this procedure? It's laborious, so I don't want to do this over and over again. Yes?
I was wondering, why did you use the other equation, x5, equal to 20 minus x1? Is it because that have a higher bound?
Okay, so that's a question whose answer would suddenly illuminate things. So I'm going to reserve that for now. You had another question. The same thing. Okay, so why not use this? After all, this looks more pleasing, more convenient. And the problem is, if you use this, you get x1 is 20 minus x5. Okay? So you will see that, okay, so suppose we use this. Okay? So remember that x1 is now expressed in terms of x5. So x4 is now going to be in terms of x5. x2 is now going to be in terms of x5. Okay? And x5 is still a basic variable. So if you go back to our rules, we want every basic variable to occur exactly once in any equation. Okay?
Well, I'm not getting it.
Okay, so let me do this one more time. If you use this equation, x1 is expressed in terms of x5. Okay? If you plug in that value of x1 here, you would get x4 in terms of x5. So x5 would occur here, here, and here, and it is still a basic variable. It's still a dependent variable. And so it doesn't satisfy the properties that you wanted of your dependent variable, which is that you want every dependent variable to occur exactly once, and every equation to have exactly one dependent variable or basic variable. Okay. Now, one may just extend your question, which is, why have these rules in the first place? And so you have these rules for now, just take them as rules. But you have them because this makes it particularly easy to evaluate the consequences of any change that you're making. Okay? And it'll become apparent to you as we go along. The reason for using this equation is because it is this equation that loses a basic variable and that gains a basic variable. Right? This equation, now the basic variable instead of x4 is going to be x1. So when you make this change, you still have exactly one basic variable corresponding to this equation, and it will be expressed in terms of the new non-basic variables. So this is the right place to start. Okay. Should I say this again?
Isn't the short answer, though, really would start out by saying that it's constrained only by x going up 5? I mean, that's really the short answer, though, right? I mean, that's how we would determine it.
That's how you would determine it, but the why is because if you use anything else, you don't have a representation in a convenient form. And they had a question as to why you do that. So I think it's, in addition to learning the recipe for solving these problems, which is the least important part of the course because we have efficient software packages to actually solve these problems for you. It's actually more important to understand what we're doing. And the hope is that once you understand this method, which is relatively well understood, then when you are faced with a new problem, you have enough training to think about new methods that address those problems. Okay, so again, we have x1 in the form that we like. And now, let me just rewrite this. So x5, which was 20 minus x1, is now going to become 20 minus this quantity. And if you simplify, you get 15 plus 1 over 4 x4 plus 3 over 4 x3. Okay? And notice that this equation, which is 20 minus x1, it has x5 as a basic variable, and now x1 is also a basic variable. So we have to rewrite it, and when you rewrite it, you get x5 in terms of the new non-basic variable. So this is going to be one of the equations. This is going to be one equation. Similarly, x2 you're going to rewrite, and the z equation you're going to rewrite. The rewriting is wherever you see x1, plug in what you found. Okay. Yes?
I think the equation on both should be plus 3x3 and plus 3 for the x3.
Oh, sorry. So this is plus 3x3, and this is thank you. So just fix this thing. I just made a numerical error. So is everyone comfortable with this transformation? Okay. So let me write the new set of equations and so let me do that here. So after you do all of these calculations, you end up with the following. x2 is 10 minus 1 over 4 x3 minus 1 over 4 x4. x1 is 5 3x3 over 4 minus 1 over 4 x4. x5 is 15 plus this, and z now becomes 40 minus 5 over 4, 4 plus 3 over 4 x3. Okay, so this is our new system of equations. It captures the solution where x3 and x4 are set to 0. And if you set x3 and x4 to 0, you get x2 equals 10, x1 equals 5, and x5 equals 15. Okay. And the value of the objective function at that solution is 40. So that's what this is. So are we done? We can still increase the objective value, it seems like it, right? Because x3 has a positive coefficient. So this last equation, not only does it say that the current objective function value is 40, it also says if you increase x3 by 1, you earn 75 cents. So why not do that? So again, observe that in the original objective function, the original objective function had nothing to do with x3. It has 0 value for x3. Okay? Because it is 2x1 plus 3x2. Now, as we go along, when we make these transformations, somehow we figured out a profit of, we figured out how to make money by increasing x3. So how can this be possible? Does everyone understand the question? So in the problem that we started with, we said the objective function value is 2x1 plus 3x2, right? That's the objective function we started with. We said if you increase x1, you get, for every, whatever x1 is, you get paid 2 for each unit of x1. And you get paid 3 for each unit of x2. If you look at this, this says, by changing x3, you get paid 75 cents by increasing x3. The question is, how is this possible? Originally, we got paid nothing for having positive x3, right?
Because we have 3 other equations, especially number 2, like there's a relationship between where's the relationship between x3 and x1, x2 from equation 1. So somehow that relation helps.
Okay, so very good. So the answer is that x3, there's a relationship between x3, x1, and x2, and somehow that's the reason for what we are observing. The answer, of course, is that's right. Notice that if you change x3, you're going to have to change x1 and x2. Okay? Let's actually understand what effect that has. If I increase x3 by 1, what happens to x1? x1 goes up by 3 over 4. What happens to x2? It goes down by 1 over 4. So if you increase this by 1, you're going to get paid 2 times the increase in x1, right? Which is 1.5. But you're going to lose 3 times the decrease in x2. I think I see a lot of puzzled faces. So again, nothing about the original problem has changed. Okay? You still get paid $2 for any x1 and $3 for any x2. For instance, here x2 is 10, so you get $30 from x2, and you get $10 from x1. That's how you get the 40. Is this clear to everyone? Now, the reason why x3 has a positive coefficient here, it can be explained in the following way. Changing x3 forces you to change x1 and x2 in some way. Right? The precise way in which you have to change is described by these equations. So if I increase x3 by, so if x3 goes up by 1, this implies x2 has to go down by, x2 goes down by 1 over 4. Okay? And x1 goes up by 3 over 4. So when x2 goes down by 1 over 4, this means we lose 3 times 1 over 4, right? Because for every unit decrease of x2, we lose $3. So if it goes down by a quarter, you lose 3/4. Whereas here, you gain 2 times 3 over 4. Okay? And so the net effect is that, so you gain 2 3/4, but you lose a 3/4. Therefore, your net increase is 3/4. Okay? And instead of doing these calculations yourself explicitly every time, having this last row just captures this. This is what it means when you say increasing x3 by 1 gives me $3 over $4. It's not that you get paid for increasing x3, you still get paid from x1 and x2, but increasing x3 by 1 changes x1 and x2 in a certain way. You have to give up some x2, but you can increase x1 by much more. And that somehow gives you a profit of 3 over 4. So it's just to explain these coefficients and where they come from. You do a similar calculation for x4, you will see that on balance you lose $5 over $4. Is this clear to everyone? If there are any questions, I'd be happy to answer them. Yes?
On the first step, we say that the x2 has to increase of 5, and then we have the calculus of the other variables.
Right.
Why didn't we do the same here?
We've done the same. So the question is, in the first step, we said x2 goes up to 5, then we rewrote things. The second step, we said x1 can go up to 5, and we rewrote things. Now we are here, and we have to do the same thing. So I just wanted to illustrate something before proceeding. We're going to continue. So here, this is the only choice. Do you agree? You have to increase x3. Okay? Now when you increase x3, what happens? Which equations limit you from increasing x3? This says x3 can go up to 40. Okay? This says x3 can be increased by any amount. This says x3 can go up to 15 divided by 3 over 4, which is 20. And of course, this equation is now going to be your key equation. So once again, you're going to move x3 here, x5 here, express x3 in terms of x4 and x5. Once you have that, so let me write just that down. So this, from here, you will get x3 equals 20 minus 4 over 3 x5 plus 4 over 3. I think it's 1 over 3 x4. Yes.
But that number as a fraction. So, yeah.
3 over 4. 15 divided by 3 over 4. Okay, anyway, so you rewrite x3 in terms of x4 and x5, and then you plug in that expression for x3 wherever it appears in your system. Okay? And you end up with the following. So let me just write down the final answer. You can do this calculation yourself. So let me write it here. So this is the final set. You get x2 equals 5 plus x5 over 3 minus x4 over 3. x1 is 20 minus x3 minus x5. And x3 is 20 minus 4 over 3, 5 plus 1 over 3, 4. I'm thinking maybe, so it may be that I made some calculation error in this. Somebody can check it. Okay? But the point is that finally you end up with something. So let's, yes.
Then x3 appear on both sides of the way you wrote it?
Yeah, so this must be x4. Yeah, I'm positive that there's an error somewhere. So I think I made a mistake in my calculation. So let's not worry about the actual numbers. You can find out what these various coefficients should be. So let me just say this has a mistake. But let's actually get to the main point, which is suppose you end up with something like this. Okay? Then what happens? So this says you cannot increase it any further, right? That no matter any change, no matter what change you make, you have to decrease your objective value. Okay? And does that show that this is an optimal solution? Yes. Why? Okay, well it certainly says that if this is the problem that I give you, suppose your problem is to maximize 55 minus x4 minus x5 subject to all of these, then clearly you would set x4 to 0, x5 to 0, and everything else is fine. For this particular problem, that is an optimal solution. That I agree. But how do you know that you get an optimal solution for the original problem? After all, we don't care about this problem per se, right? Yes?
Because each time the problem was equivalent, this linear thing.
Okay, very good. So the reason why this solves the original problem is because when you go from one step to the next, you preserve solution. Okay? And therefore, at the end, you get a system of equations which is exactly the same as the problem that you started with. And therefore, you get an optimal solution. So, the summary is that once, as you start doing this, ultimately, if you end up with a set of equations that look like this, then you have solved the problem to optimality. Any questions about any of this? Yes.
What's the interpretation of this method in terms of the linear algebra?
So the question is, what's the interpretation of the method in terms of linear algebra? So let's actually postpone discussion on that. So we will see that all of this can be done in about 15 minutes in terms of matrices. And you will see that treatment also. Any other questions? Okay. Now, so let me summarize where we are. You give me any linear program, I will convert it to standard form, then apply this method, and we know that if it ends up with something that looks like the last set of equations I wrote, then we have solved the given problem and we found an optimal solution. Okay? This, everybody agrees? Okay, you had a question.
So if we go, for example, if we look at all the variables and then we couldn't get to a form like, just subtracting, we couldn't get the optimal solution, that means the problems are solved.
Okay, so I won't retake your question because that's what I want to say next anyway. Is what are all the things that could go wrong with it? I mean, we took an example that happened to, we did 3 or 4 iterations with some mistakes, but somehow we ended up with something good. So what might go wrong? Yes?
I'm just thinking like if you write a program to calculate this, you're gonna end up with writing a lot of loops, and it's just a problem like programming perspective. You end up like an endless loop. Like every time you get the same thing again.
Okay.
So the loop never ends.
Okay. So never ends. That's a nice way to put it. So let me get rid of this. So the first problem is, how do you know that this actually ends? Maybe you're doing this till the end of the universe, right? That could, there's nothing that says that can't happen. After all, we only said if we keep doing this and if we end up with something like that, then we stop and we're happy. So, does it end? What else may be an issue? Sorry? It should end. Why?
There are only limited possibilities of this kind of operation.
There are only, okay. So, that's a good observation. So, the observation is that there are only a limited number of possibilities of this stuff. Okay. So notice that if I give you a choice of basic variables, there's exactly one way to write your system. If I tell you x1, x2, and x3 are basic, okay, so I just tell you that, then there's exactly one way to write your system. Okay. And how many choices of basic variables are there? For this problem, out of 5, you have to pick some 3. And in general, out of some n, you pick some m. There are finitely many. So, maybe one way out to address this is the following observation. So there are finitely many descriptions. So let me say finitely many choices of basic variables. Okay. Which means, by the way, the system of equations that I wrote down, it's called a dictionary. Okay. So there are finitely many dictionaries. Okay, so the fact that there are finitely many objects, does it mean that this will end? After all, okay, it is true that there are finitely many objects. Therefore, to solve a linear program, you just have to enumerate all possible choices of bases and check whether that representation gives you all negative coefficients for the objective function value. Okay? This is a finite algorithm to solve linear programming problems. So I give you that. But this doesn't answer the question that we started out with, which is, does this procedure that we said goes from one dictionary to another dictionary, from that dictionary to yet another dictionary, and so on, does that end? And these are different questions because even when you have a finite set, if you're not clever about going through its elements, you may end up revisiting something that you already saw, and you may end up in an infinite loop, and that's the problem that was alluded to. So while this gives you an algorithm to solve linear programs, it may not be a particularly good one because it involves checking all possible choices of bases. And if you have a million variables and hundreds of thousands of constraints, then this may be impractical. Nevertheless, this is a finite procedure that will end, that will always give you an optimal solution, assuming one exists. Okay. But the first question that was posed still remains. Okay. Yes?
When we move from one dictionary to another, we find the value of one variable, so the number of the variables defined is strictly decreasing each time we change the dictionary, so in the end we will find out the value of the finite number of steps.
Okay, so so this answer attempts to address the procedure itself and argues that somehow the procedure has to end because when you go from one dictionary to another, you find the value of a new variable. Now the difficulty with that argument is that it is true you find the value of a new variable, but you find only a value for it. Right? In future iterations you may increase its value, and a variable can assume infinitely many values. Now there's another argument that one can make that's sort of closely related to what you said, which is as you go from one iteration to the next iteration, you always increase the objective function value, right? Initially we had 0, then we moved to 15, then we moved to 40, and then we moved to 55. So we always go up. But that also does not answer the question whether it ends, because you could keep going up without actually stopping. So I could go, it's possible for me to go 1, 1.5, the next to 1.75, and keep on dividing the increase by a factor of 2. So your increase is going to be positive, but only 1/2 of what it was. You will not even get to 2. So it is a question, right? I mean, it's not trivial to conclude that this procedure will end. Now, what's worse is that we may not even know how to begin. How do you begin? How do you know that there's a feasible solution? Does that seem like an issue? If I give you a linear programming problem, I mean, I picked a particularly easy one because I wanted to be able to solve it easily. But there's no reason for an initial representation to be feasible. So here we said x1, 0, x2, 0, I get x3, x4, x5 positive. But what if x4 comes out to be negative if you do that? Yes?
Actually, this is what I observed here, like why you didn't take like x5, like, I mean, just do the x1, I pick x1 to the left and x5 and to the, like, nothing.
Well, actually, okay, so this question here does not have anything to do with the discussion now. So this will become, so when you work through a couple of examples, you will see the utility of not doing what you said.
But this is kind of like beatable thing, like what you just said.
No, not really, actually. But it is, so in other words, suppose I give you a huge linear programming problem, which has no solution. I mean, this method assumes that you start at some solution, then you go to the next one, then you go to the next one, and so on. If I give you a problem with no solutions, where do you start? How do you know that there are no solutions to this linear program?
Maybe in linear algebra technique, if we can't invert some matrix, then it's not going to work.
Okay, so that's a good answer. Is there some way, some other way for you to somehow infer that there are no solutions, and you will begin only if there are solutions? And this is sort of what you're saying. Yes?
You can try to represent constraints as a system of equations and solve them simultaneously.
You can represent constraints as a system of equations and solve them. Okay, which is sort of the same answer that was given. So somehow use a linear algebraic method to conclude that there is at least one feasible solution. So what you're saying is if you look at the underlying system of equations, and if that system of equations has no solution, meaning there's a certain matrix that cannot be inverted, then you can conclude that there are no solutions. All good answers, but again, the point is, before you even begin, you want to make sure that there is something for you to do. And the procedure that I've described so far does not address that. It only says, you give me a starting point, which is this feasible dictionary type of thing. All I know is I can check whether there's a way to improve and go to another dictionary. I can keep on doing that. And if I end, you have an answer. So we don't yet know how one begins this procedure. We don't have an assurance that it ends. All we know is that if it ends with an optimal solution. Does that make everybody, does everyone agree with that assessment of what we've done? Okay. So we want to address two questions. One is to somehow argue that using the same ideas, one can actually begin the procedure. That somehow you give me an arbitrary system of equations and inequalities, I can somehow find an initial dictionary so that I can apply the procedures that we know. Then the second point that we'll get to is a proof that this procedure actually terminates. Now it turns out that, as stated, the procedure may not terminate. There could be what's called cycling. So even though there are finitely many choices of basic variables, lots of things could conspire and cause you to go through the same sequence of dictionaries over and over again. Now, for this to happen, you have to use pathological rules to decide which variable enters and which variable leaves when there are ties. So there were a couple of questions about how you will choose the entering variable when there are many positives, and how you will choose the leading variable when multiple rows achieve the minimum simultaneously. So if you're not very careful about making these choices, you could cause this method to cycle. So what I've specified is not a method, it's a family of methods, each one different depending on how you choose to break these ties. Now, the good news is that there are easy tie-breaking rules that assure the existence of, that assure the termination of this procedure, assuming there's an optimal solution. So the answer to this question is that if you're careful about choosing your entering and leaving variables whenever there are ties, there is a way to make sure that this procedure terminates. And when it terminates, you get an optimal solution. Okay? So in the next lecture, we spend the first half talking about issues having to do with initializing this method and determination of this method. And the second half of the lecture, I'll just show you how one solves this problem in Excel. Thank you.